kinds of friendly faces. Welcome. It feels like a new music concert, and Alan knows what I'm talking about, which is you're resonant with that frequency of new music. It's usually me, my two kids, my cat come to the concert. So this is actually much better in that respect. But all joking aside, I think it's wonderful that we're having this event here, and Drs. Yoon and Lou have been working really hard, and it really sort of resonates with what I do and what I think Purdue can become as a music department, and bringing in the engineering and sciences, and from STEM to STEAM to STEAM with an H, the humanities. And as you probably know, they won this impressive grant from NSF. I think it's $900 million, $900,000, which is really impressive. As you probably know, it's very difficult to get it from this collaborative arts, where arts meets engineering. So really happy that this is happening. And without further ado, Dr. Yi.
So I always like infusing
Sorry. My apologies.
I always like infusing some other art in my performance. So sometimes I played with dancers dancing on the same stage, and also sometimes I projected some pre-made images relevant to music in my concert. So those are more like to attract more audiences and also to make concert a little more entertaining. As AI is emerging, I started to think, how about having AI generate automatically the relevant images to music when it analyzes music. I have been working with students with various backgrounds in music, computer engineering, computer science from last semester, and I really appreciate their work, time, and effort. Thank you so much. I'm also very grateful for Create Grant by Liberal Arts, and also SERVE summer program by ECE to support this interdisciplinary project. I'm going to play some cello solo pieces to feature this technology. Those pieces are quite diverse actually. So I will play pieces by Afro-American, Asian American, the Mexican, Spanish, and also traditional German composers. So you will hear various sound. And this technology is actually the ongoing and in progress. So if you could give us a little more actually feedback after the concert, I will appreciate that. Now I'm gonna actually say just I'm going to actually just give rough ideas of the process of this project. Then later Tim and Josh will speak of details of the technology. So tools like basic pitch and spectrogram will make feature matrix when they hear music. Then those feature matrix the feature matrix will be the feed in as the input to train neural network and support recognition. Then those models then will make prediction of subgenre of the piece and also the emotional changes. Then those prediction will generate text prompt. The text prompt, the pitch described music will then feed into stable diffusion. Then stable diffusion will actually generate the relevant images. Then while music is played, then the images will be updated. So I hope you enjoy the next piece as well.
We are the two student leaders on this research project. So the basis of this project is within the intersection between visual art and audio art music, right? And the idea is that both of them can evoke emotions to the listener or the viewer of the piece of art. And the way the music does that is generally a function of each of the features within the music. So be that the harmony, the rhythm, how fast notes are being played, how loud they are. All of these features within the music kind of suggest the emotion that the listener should be feeling. On the other side, within visual art, emotion is largely a function of the lighting and the colors within the piece of art. So here is just like 4 different pictures of a guy sitting in a chair. And so the subject is the same, but yet through different lighting and colors, you can see that each of them convey pretty different emotions.
Okay, so generating art in real time as a music accompaniment is just a very hard task in general. Like if you want to generate art in real time. So that, lucky for us, there's already a diffusion type model which is basically called stable diffusion. And basically what we can do is we can feed it text and it will give us an image. And then, I mean, if you give it a small prompt, it'll give you an okay image, but there's a new field of engineering called prompt engineering. Basically, we're figuring out how can we add more information to this prompt, how can we make it better so that Stable Diffusion gives us a much better quality image of what we want.
So the general idea with this project, like Professor Yoon was kind of getting into earlier, is to be able to take some audio input and then create an adapting video output that is a piece of changing visual artwork. The way that we do this using machine learning is to first extract features from a piece of audio, and these are just pure numbers that describe that piece of audio that a computer can understand, and then use those alongside machine learning models like neural networks to generate emotional keywords that describe the piece of music, and then also find like the genre of the piece of music, which can serve as a basis for the subject of a piece of artwork. String together a prompt that we can send to Stable Diffusion and then generate an image for every couple of seconds or even less than a second of audio input that we get. It obviously ends up being a lot more confusing than just that straightforward set of like 5 different tasks, but we'll get into each of them briefly.
Okay, so one of the first things you need to figure out when you're creating a system to process music in real time is how can we get the music to be in some representation that a computer can understand. So there's 2 main methods we can do that. The first method is if we have some software, we're using Spotify's basic pitch. If we have some software that can convert the incoming audio to MIDI, then this is a very easy way that we can basically process it, because MIDI stores basically the pitch of the notes, the rhythm, and it stores velocity, and you can store other things, but we don't use those by default. And basically you could do very easy manipulations to like find chords, find keys, find whatever patterns you want in terms of the runs. And the other representation we have is called a spectrogram. So basically you calculate the frequency in the input signal over time, and then you display them in a graph, and this provides a lot more information about the timbre of the instruments that is playing, and it encodes some pitch and rhythm information, but it's not nearly as precise as a clean MIDI output. And so one of the things that I was doing over the summer is I was writing a program using this technology called Spotify's basic pitch to basically you feed it an input signal and it will tell you what chords are currently playing in a it basically uses a sliding window approach where you basically take the last n seconds of audio and then you do some math using MIDI, and then we can figure out the chords. And the general idea we wanted to do with this is we wanted to take the patterns of these chords and we wanted to feed them into a type of neural network called a transformer, which basically allows us to draw conclusions between the patterns of chords and the output emotions or output genres. But unfortunately, that's kind of on hold right now because the data set required to do that would be like several hundred terabytes in size and probably several $1 million to collect everything, so we need to figure out a better way to do that. But yeah.
Alright, to get into the models that we use briefly, starting with our classification neural network for genres. This is how we're predicting the genre of a piece of artwork. Obviously, you've noticed we're only working with classical music right now, as that is what Professor Yu plays. So we are predicting a genre within classical by kind of narrowing it down to a certain time period. The 4 kind of overarching time periods we're working with are Baroque, classical, which is a misnomer, but it's a certain time period as well, and then Romantic and 20th century classical music. So once we have these large set of features that we extract from our MIDI data and from the spectrograms that represent the audio, we select ones that have a strong correlation with our desired output, and then we use those as input for a neural network that is trained on a large set of data where it's just seconds, clips of audio that are labeled with the genre that they come from. And so the neural network learns what kind of values for each of these features correlate to which of these genres, and then given a new piece, can predict what genre it falls into. On the other side, when we're trying to predict the emotions that a clip of audio conveys, we do that by making a regression, which is just predicting a single numeric value for 2 different labels, basically, arousal and valence, where valence is how positive or negative emotion is, and arousal is how intensely it's felt. So in our data, valence and arousal values scale from 1 to 9. So valence and an arousal of 1 would suggest a very non-intense emotion that is very positive, and then 9 on the other side is like a very intensely felt emotion that is negative. So once we have all of these values, we kind of, in like a Mad Libs style, throw together a prompt to send to Stable Diffusion. So like I was saying earlier, the subject of the piece is described by the genre that we decide that the piece of music is from. So in our current prompting style, we just tell Stable Diffusion to depict like romantic classical music, if that's the genre that we chose. And then we'll tell it style of an artist to imitate, because our work generated by Stable Diffusion can be heavily influenced by the names of artists in the prompt. So we'll choose a visual artist from that era of time as well. And then, as I was saying earlier, the emotions are conveyed through the lighting and colors in the piece. So we throw those in based on the valence and arousal values that we get.
So all of these technologies are great, but there's also quite a few practical considerations we have to take in when we're trying to actually build a finished product which actually takes the music and generates video in real time. And basically the largest consideration we have to make is how do we split the computation so that it all runs efficiently on a normal size computer. So basically the way we did this is with multi-threading. Basically each of our different calculations, like our feature calculations, our neural network predictions, all of them run in separate threads, and we have this awesome architecture that basically allows us to send the results from one to another, so we're not holding up like one task based on the results of another. And this also offers scalability, because if you want more frames per second, just make more image generation threads and assign one to each GPU or something like that. But yeah. So in terms of future work for this project, the first thing is something that I mentioned earlier. We want to, if we find a way to do this efficiently, we want to be able to take patterns of chords and we want to create a transformer type neural network, which can basically say, given a pattern of chords, what is the most likely emotion and genre values that come from this pattern of chords. And we also want to achieve higher parallelism, because like even though we have the threading architecture right now, there are still lots of improvements we can make to it. And
yeah, and then furthermore, just expanding the usability of this. One big thing that will make the generated videos a lot smoother and maybe more accurately reflect the emotions that you might feel would be to use image-to-image diffusion. So basically, Stable Diffusion, given a text prompt generates an image. There are other tools out there, one called Deform that we're looking at, that can generate an image given a different image. And so we could use this to basically connect our images together and create a more understandable story through the images that are being presented. Furthermore, we'd like to expand to all genres of music. So instead of just working with classical music, we can predict some imagery for a piece of like EDM music or jazz music. And we think that we could actually expect much better results with these kind of more varied genres, because you can expect, you would maybe, should be self-explanatory that a computer would have an easier time distinguishing between jazz music and electronic music than between romantic classical music and Baroque classical music. The last thing that we want to do is to kind of ditch the current very cookie cutter Mad Lib style generator or prompts and introduce more variation by using some large language models. So these are tools like ChatGPT that kind of think on their own and can generate something that's a little more interesting than just telling it to depict Baroque classical music. So we could say, here are the emotions that should be conveyed, and then here's kind of the era or the style of the piece. Give us a prompt to send to Stable Diffusion, and it'll come up with something a lot more interesting. And so these are all of our kind of directions going forward. But I'd like to just say a big thanks to everybody that worked on this project so far. We have the whole team from the summer. Paul and Brian are here, as well as, of course, our professors, Yoon and Will. So yeah, thank you very much, and we'll be back into the concert.
Bravo.